What is calculus? Well, simply put, calculus is the mathematical study of continuous change. There are two primary branches of calculus. Differential calculus, which is what we'll focus on first. I call this the Calculus 1 subject. And then later on in these live lessons, we'll dig into integral calculus, which is a focus of what I call the Calculus 2 subject. So right now we'll focus on differential calculus. I'll go over a detailed example to help you understand exactly what this is. And then we'll do one quick slide on integral calculus at the end of this section so that you have a sense of what that is, and we'll come back to it in more detail later on. To help you understand what differential calculus is, I'm using a silly example and an illustration, which if you've seen any of my content before, that is a trend, that is something that I like to do. So differential calculus is the study of rates of change. And my specific silly example that I've illustrated here is one where we're considering a vehicle traveling some distance d over time t. So the vehicle starts at home and minutes pass, about 15 minutes here, and over those 15 minutes, the vehicle travels more than 2 kilometers. For the sake of simplicity, I only have the vehicle traveling away from home, away from the origin, but you could make this more complex and have some other examples where the vehicle starts to come back towards home and then distance could say go down. But let's just assume in this case that we're traveling away from home, and so we start at time 0, having traveled no distance, and as time goes on, we travel further and further away from home, but at different speeds, at different rates of change. So let's dig into that a little bit more. Let's say that at the very beginning of our journey, we drive to a shop down the street. So we accelerate away from home. So our distance over time initially as we leave home is very small. But then as we accelerate, as the car starts to move more quickly, we see that the distance traveled over time begins to increase. The slope of this line begins to increase. And then when we reach the shop, we slow down and stop. And it takes us about 5 minutes, so the vehicle is stationary while we're in the shop buying some snacks for our trip. So yeah, we slow down and then we stop at the shop. And so for about 5 minutes here, from the 5-minute mark to the 10-minute mark, there is no change in distance away from home. We're at that about the 1 kilometer mark for several minutes here. And then after we've picked up our snacks, we start the car moving again. We accelerate onto an on-ramp. And once we get onto the freeway, we put on cruise control. And so we have this constant speed that we're traveling away from home for this period here. We can dig into this even a little bit more. So during that initial acceleration away from home, from the vehicle's origin, we could put straight lines, tangent lines, at any given point. So perhaps at the 1-minute mark, we have this slope of the relationship of distance over time, and then at the 2nd minute, we have this steeper slope of distance over time, which means that we're going more quickly. And then say at the 3-minute mark, we have an even steeper slope, meaning that the speed of the vehicle, the distance traveled over time, is even faster. So when distance over time is increasing like this, when the slope of this curve is increasing, that's acceleration. When we get to the shop, at any point, at any of those time points that we're at the shop, when we draw this tangent line, the vehicle is completely stationary, and that corresponds to a slope of 0 distance over time. And then jumping ahead to the point where we are traveling at a constant speed on the highway, at any point that once we have that cruise control on and our vehicle is always traveling at the same speed, at any point along there, it already is a straight line. And so at any point there, when we try to draw this tangent line, this straight line to the curve there, we will always get the same slope because the vehicle is traveling at this constant speed here. All right, and just tying all that together into one chart, we've got that initial acceleration. So the slope of distance over time is increasing here at the beginning. Then when we get to the shop, the vehicle's stationary, so the slope is flat. And then finally, that final stage where we have cruise control on the freeway and we don't have any acceleration, but we do have this constant speed, this constant change in distance over time. Up to this point, I've been talking about just by eye, drawing a straight line, a tangent line, at particular points on the curve. And that's what I did. So all of these orange lines, this red line, this green line, those are straight lines that I just drew by eye at particular points on the curve to illustrate a point. But if we wanted to, we could formally calculate the derivative at any given time point. So if we know the function that describes the curve, the brown curve of distance over time, then we can formally use differential calculus to calculate the derivative of that function. And then, once we have that derivative, we can simply plug in any given time point, and that derivative of the function will provide us with the exact slope at that point on the curve. This means that instead of eyeballing and drawing by eye these straight lines, we can have a very specific, very formal understanding of exactly what the slope is at any given time point t, at any given minute in time, any given second in time. A common convention is to use m to indicate slope, the slope of a line. And so here I'm using m at our various time points and showing a slope. Now I've made up these numbers. They're not necessarily very exact. They're just to illustrate a point here. But as you can see in that initial acceleration phase, our three orange lines have a gradually increasing slope. So that first tangent line that I initially drew by hand, but we could actually use the derivative of the Brown function to calculate exactly what the slope is at this point. And so it could be a slope of half. So at, say, the first minute mark with a slope of half, that would indicate that we are traveling half of a distance unit per time unit. And then where m is equal to 1, for every unit of time, we travel 1 unit of distance. At m equals 2, for every unit of time, we travel 2 units of distance. And then here, when we're stopped at the store, our slope is equal to 0, which means that it doesn't matter how many units of time pass. When we're at this phase where m equals 0, there's no distance, there's no change in the distance traveled. And then finally, for our green line, our green slope, let's say again here m is equal to 1, the same as here when we were going to the store. And so here again at any point here where m is equal to 1, the distance, we travel 1 unit of distance for every unit of time that we travel here. Now, this goes to show how silly my example is in some ways, because it means that on our way to the store down the street, we were going twice as fast as we were on the freeway, but hopefully you'll forgive some of my silly things that I'm doing here, some of these oversimplifications. Maybe I was really in a rush to get my snacks that day. Drive safe, folks. Okay, so now I've made my chart smaller on the left here and added some summary information all kind of into one spot. So we've got the same slopes m at those 5 points over time. And more formally, I'm going to describe that slope m now as the change in distance divided by change in time. And so that's equal to speed s. So we can obtain this speed s, this change in distance divided by change in time, by, as we mentioned earlier in differential calculus, taking the derivative of the Brown function of distance over time that underlies these 5 slope lines. Now things get really interesting. So not only can we take a first derivative with differential calculus, we can take multiple of them. So now, if we were to take a chart of speed over time, so let's say kilometers per minute, That's a measure of speed, an unusual one, but it is nevertheless a measure of speed. And so now over time, this is the same journey that we were making with distance over time, but what we're doing here now is I have this blue line that describes speed over time. So for example, when we're at the store where slope is equal to 0, now speed is equal to 0, so m and s are equal to each other here. S over here is the same as m over here. Speed is the same as the slope here. So where a slope is 0, this means our speed is 0, and so at these minutes that we're at the store, there's no speed. We're completely stopped. But on the way to the store, we had this increasing speed from home, and then as we approached the store, we slowed down. And then same thing, after we were in the store, our speed increased gradually until once we were on the highway and in cruise control, we had this constant speed. So this might be a good spot here, if you haven't followed along with all of this, to pause the video and just have a look at how, with distance changing over time on the left here, how that corresponds to changes in speed over time. And you can prove to yourself how the slope changes at each of these 5 points correspond to a particular point on this chart of speed over time. So our fastest point was this point here on our way to the store where the slope was m equals 2, so that we briefly touched this speed of 2 kilometers per minute before slowing as we reached the store. So we can use the first derivative of the Brown function, the distance over time function, to give us the speed over time. Focusing now exclusively on our chart of speed over time, we could now, by eye, calculate what the slope might be by drawing tangent lines at any point in the curve. Or alternatively, we could calculate very precisely what the slope is at any point on this curve by taking the derivative of this speed over time. So this is now the second derivative of distance over time. So the first derivative of distance over time gave us speed over time, and now the second derivative allows us to identify acceleration over time. So at this point here, at about the 1 minute mark, our acceleration corresponds to 1 unit of speed over time. And at this later point, our steepest point anywhere on the curve, our acceleration corresponds to 2 speed units over 1 unit of time. And then as we approach the store, our acceleration becomes negative. So when we slow down, anytime our speed is slowing down, there's a negative slope, a negative acceleration. At the store, our acceleration is 0. So not only is our speed 0, but at the store, our acceleration is also 0. Now, interestingly, after we speed back up, so we accelerate back onto the freeway, there's this interesting point here where our speed is reasonably fast. We're traveling at 1 kilometer per minute on the freeway, but our acceleration is 0. Because we're in cruise control, our acceleration isn't changing, and so the slope here is flat again. So both when we're stopped, as well as when we're traveling at a constant speed, in both cases, the slope between speed and time is 0. And to throw a little bit of math on this slide, so this slope m now, in this chart, corresponds to a change in speed over a change in time, which is equal to acceleration, and that can be represented in kilometers per minute per minute. Pretty cool, right? So I know it was a silly example, but hopefully it drove the concept home of what we can do with differential calculus and how you can take a derivative and even a second derivative to study the rates of change of a phenomenon. Returning to the what calculus is slide that we started this topic off with, hopefully you can now see how calculus is the mathematical study of continuous change, how it provides us with tools for studying how some phenomenon changes over time. And so far, we've only talked about the differential calculus branch, but let's quickly jump to an example of integral calculus, just to show you what that is relative to the differential calculus that we've been studying so far, so differential calculus, we're taking derivatives. With integral calculus, in a way, we're doing the opposite. So it's the study of the area under curves. And yeah, it kind of facilitates the opposite of what we can do with differential calculus. So with differential calculus, we were able to take a chart of distance over time and convert that into a chart of speed over time. With integral calculus, we can do the opposite. We can take this chart of speed over time and then calculate the area under the curve, and that will correspond to the total distance traveled. So for example, at this point here, where we're at the store and stopped, there's no area under the curve, and so there's no distance being traveled. Whereas once we're on the highway or on our way to the store, there is an area under the curve, and that corresponds exactly to how much distance we've traveled in this chunk under the curve. All right, so that was the beginning of our orientation to calculus. I hope if you didn't already have some understanding of what calculus was before, that now you have an idea of what it is, as well as how differential calculus is different from integral calculus. Up next, we have a fun section on a brief history of calculus.